So I had a couple of better drawings. This is of course it's upside down from the way I drew it. That just means that I took this from Wikipedia. That just means that their sign convention is reversed, right? They're talking about tension positive, okay? But nevertheless, then this is a nice computer drawing of what type of yield surface? Drucker-Prager. Right? Drucker-Prager. And this is what? More Coulomb. Okay. So we can go on adding complexity to infinity, right? I mean, we can go on adding complexity such that you might end up with something like this. And this is called the Sandia geomodel, or Kayenta. This is a generalized plasticity model in the sense that by turning off parameters or setting parameters to 0, you can recover all of those other yield surfaces that we talked about. Drucker-Prager, Moore, Coulomb, von Mises, standard J2, or Tresca. You can recover all of those yield surfaces. But you can go on and add more and more parameters up to something like 69 parameters, which would mean that you'd have to do like 69 independent experiments to fully populate this model. But it can exhibit very, very complex behavior. So I don't know if you can see from this picture, but this comes down to a cone, just like the Drucker-Prager and Moore Coulomb models. This comes down to a cone such that in tension, there's a difference between compression and tension. But you can see, looking down the hydrostat, it actually has a more complex shape than those other ones, right? It's not just a circle or a hexagon. So it has a little bit more complexity there. And then also, if you look at a cross-section, so if you just slice this thing down the middle and you look at a cross-section, then this is what you see. So it comes to a cone or a point in tension. But you'll also notice, if you look carefully, that the shape on this side is not the same as the shape on the other side. And that's in its ability to model deformation-induced anisotropy. So this would be due to anisotropy. So because I can have the same magnitude of the stress here or there. In one case, I'm elastic, and in this case, I'm plastic, right? I'm yielding. Okay. We use the word plastic when we're talking about geomaterials, but again, it really should be inelastic, right? This could be due to pore collapse or some other thing. Also, this model has a cap on it. So this is the first model we've seen that has a cap on the end of it. So all of those other models were open to infinity on the one end, meaning as I increase the pressure, the material just gets stronger and stronger and stronger. Okay? What this, with the cap on it, means if I increase the pressure, eventually I'm going to hit the cap and I'm going to start yielding. Okay? Now, you can also have the functional dependence on the cap such that as you continue to yield and continue to accumulate plastic strain, you push the cap out. So the cap, just like the yield surface can grow, and in this case it can grow anisotropically, right? It can grow this way, it can grow that way, it can grow isotropically, it can grow all at once. It can also grow this way. It can push the cap out. But the same rules apply. I mean, you're inside the yield surface, you're elastic, you're outside of it, you're plastic, and you have to have a return algorithm to get yourself back on it. So this model, again, it goes by the name Kayenta now. The guy who created this model is a guy named Arlo Fossum, and he did it when he was at Sandia, but then he left and went to work for BP for his last 7 or 8 years of his career. He's retired now, but very good mechanician. But now this is sort of maintained by a lady named Rebecca Brannon at the University of Utah, and you can actually, this is an open source model. It's written in Fortran with a very general interface. So you can go and you can then take this and hook it up to your code if you wanted to run, if you wanted to use this model. You can hook it up to your code and run it. So then I have one slide I found that's sort of a summary of all of them that we've talked about. So sort of the von Mises or J2 family at the top, and the maximum shear stress criterion family at the bottom. Of course, von Mises and Tresca, Drucker-Prager, Moore-Coulomb. There's one we didn't talk about, the Gerson model. That's for metal plasticity. And then this is, here she called it the Fossum model, but it's the Sandia-Geo model, or Kayenta. So I guess that's all I have for today. We'll get out a little early today because it's just a nice place to stop because now we're going to start talking about poroelasticity. So really we should spend all next week talking about poroelasticity theory. I'll give you your exam at the end of class on Friday. You turn it in on Monday. And that'll really kind of mark the change in the class when now we're going to start talking about the computational side and how we code up all these equations and theories that we've been talking about.